Okay, so our next speaker is Raphael Rougeot, who will tell us about the ESA Proba-3 formation flying mission. Go ahead.
And this is a remote, right?
Yes, big button advances and the top one is the...
Okay, thanks. All right, can everyone hear me? Yes. Good. Thanks. So I'm Raphael Rougeot from the European Space Agency, and I'm really glad today to have the opportunity to talk about the Proba-3 mission. So I don't know in the room who heard about this mission. Maybe see a few hands. That's good. So the mission was launched in December 2024, so kind of 1 year ago, and the commissioning was finished, successfully completed by July 2025. And now the mission is in its operational and science phase. And today I would like to report on the in-orbit success of the mission. But first, what is Proba-3? So Proba-3 is the ESA Precision Formation Flying Mission. So basically we have 3 bodies. On one end, we have the Sun, and then we have 2 small satellites. They are the size of a bit bigger than a washing machine, basically. One is the occulter spacecraft, and the other one is the coronagraph spacecraft. And the mission has to create a virtual solar eclipse in space by perfectly co-aligning the 2 spacecraft onto the Sun line. And the challenge for the mission is that the relative position must be maintained within millimeters accuracy over hours. This is an in-orbit demonstration or pioneering mission. So basically, this is, let's say, a test bench in space for formation flying to demonstrate all kinds of associated technologies. We do also rendezvous, we do formation maneuvers, and so on. But we also have a solar coronagraph with high contrast to do science. So the coronagraph is called ASPIX, and it's there, so you can see the characteristic of the instruments, but the most important one is basically the field of view. So on this picture, you can see it's a picture from LASCO C2 coronagraph on board the NASA SOHO mission, so it's one of the most successful spaceborne coronagraph. But basically, the field of view of LASCO C2 is, so in blue here, it's 2.2 solar radii. With ASPIX, we really want to fill up the gap, which means to observe up to 1.1 arson, which is really a region quite unexplored for the solar corona. ASPIX is an externally occulted Lyot-style solar coronagraph, so it's made of kind of 2 big elements. The first one is the occulter disk, which is a disk of 1.4 meters diameter, carried by the occulter spacecraft. And we have an internal occulter of 1.7 millimeter radius, which has to basically cut off the diffraction from the disk edge. And we are talking about 8% over occultation. So we have a coronagraph. We have 2 spacecraft and the Sun. But the main challenge, as I mentioned, is really the formation flying. So the coronagraph to work, we must have the spacecraft at a distance, so we call the intersatellite distance of 150 meters. So you can imagine a football pitch. And the 5 centimeter aperture of the coronagraph must remain in this black box I show here. So you see the lateral width of this box is 10 millimeters. So it's kind of the size of a grain of rice at the other end of a football pitch. So this is really the challenge for the mission. Why such a long baseline? So the idea is to improve the stellite rejection. So this is how we will get the contrast we need to observe the corona as close as possible to the solar edge, and to reduce the vigneting zone, so to get better resolution and a better throughput near 1 arson. So the mission is now successful. It's in orbit, it works, and I would like to report first about the formation performance. So I was not sure how to show you all the engineering and everything that happens to make this possible, so I just selected a random orbit, 6th of October, any other orbit could work, and I plotted here the formation control error. So this is actual in-orbit telemetry from the satellites. So the formation control error is kind of the relative navigation from the Kalman filter on board, so basically what is the relative positions between the 2 spacecraft, minus the guidance. The guidance is where the spacecraft shall be. As you can see, so the first plot in green is a relative position longitudinal error, so along the intersatellite link distance. And you can see we reach, let's say, a precision of below 100 millimeters. So here we have a 3 sigma value of 46 millimeters. But more impressively, the lateral position error, where we have some millimeter accuracy. That means basically my coronagraph is really well aligned behind the disk. Doing some statistics over several orbits, this is what we get. So some millimeter accuracy on the lateral, so per axis. Longitudinal error over, let's say, several orbits, it's below 120 millimeters. But we know we can and will improve. So we have on board a laser metrology sensor, and for several months he was out of the loop because we had to do a lot of software updates. But we believe that with this laser metrology, we will achieve something below 10 millimeters longitudinally. So basically with Proba-3, we proved that precision formation flying is possible in space. And if I go back to my graphics, this is basically what was achieved in terms of relative position. A few words about strelite rejection. So it's a spirit of Lyot conference. So this is all what you are about, after all. So for the coronagraph aspects, there was a lot of incremental numerical diffraction models to study this very long instrument of 150 meters. So we have some Fresnel diffraction from the disk, wave propagation, and then some analysis of sensitivity of the strelite rejections depending on the formation flying errors. I would like to highlight that the solar case and the stellar case are really different. Here we are talking about a field of view of degrees. The contrast to be reached is more 10 to minus 6. We don't need to go below. And we have the poster number 1 of this season, session 2 to explain the difference. I don't want to spend too much time of this plot, but this is kind of what we get from the model. So for aspects, this is a red curve. So this is a radial cut of the diffracted sunlight that we get from 0 to 3 solar radii. And what is important is to see that we have, let's say, a peak around 1 arson of 10 to minus 6, quite wide. So this is really the peak that will prevent the observation of the solar corona near the solar edge. So what we did in flight, so it's to actually, we keep the formation well, so the coronagraph is well in the umbra of the disk, but we did a 0.8 degrees of pointing. Doing so, that means my internal occulter does not cut off anymore the diffraction from the external occulter, and I have actually an image of the diffraction from the external occulter edge. So you can see here, this is the external occulter that we see on these 2D pictures, and then we do some radial cuts. So this is the colored curves here, and they really well match basically the thin black line that you can see, which is the model in terms of shape and the level. We have 30% difference at peak level, which could explain, we don't know, it's just an assumption of actually the shape, the 3D shape of the disk that we have. The level here is 10 to minus 3 because basically the internal occulter does not cut out the diffraction. Then we did other tests with various small of pointing, so below 50 arc seconds. And here as well, not entering into the detail, we see a very good correspondence of the diffraction models, where we can see on this curve, so we have a peak at 10 to minus 6 with the 2 peak structures and so on. So all those images were used to fine-tune the diffraction model that is used in the processing pipeline. So we have a very precise and good, let's say, formation to a millimeter levels and a good instrument working with required contrast. So what observations do we get in flight? So this is the first image revealed in June 2025 of the solar corona in white light. I like this image because you can actually see here still some residual of the diffraction ring. We see a lot of fine scale structures, solar wind, and so on. So that was, this image is kind of quite well processed. It was a bit for PR, but there is already a lot of science that can be done. More than an image, we can do a movie. So this one is a long-term evolution of the corona. So this is a stack of images from July to October, where we see that the corona is actually not static at all. A lot of things are happening. And then if we look at the short-term movie for the corona. So this is a movie of 3 hours long. And you can see, I don't know if you see, the video will start again. On this side, we have actually something that blows up. So in green, this is Aspix, Proba-3, and in red, it's Lascaux-C2. And so this is coronal mass ejections, which are those massive eruptions of plasma from the sun. This one is a movie, an image, sorry, not a movie. Not sure it's launching. Okay. We'll try to launch it again. Yes. So this is a small movie in the iron line where basically we have a lot of images and we do subtractions of those images just to remove the background and see the dynamic. And here as well, we see coronal mass ejections. We see some loops, magnetic loops. Here, for instance, here there are jets and so on. So there is a lot of things happening in the corona. And this is the first time we can access, basically, for hours, this region of the solar corona. And finally, this is a small animation, so a small movie in the helium line, where we see there also plasma jets from the sun. So to conclude, just to say that formation flying at a millimeter precision is now reality. So this has been achieved. It's a world first. We are really happy. So it's not only me, it's not only the ESA team. Proba-3 is a project that was going on for 2 decades almost. It's 15 countries, more than 15 countries, including Canada, and more than 40 industries. We have a good instrument, so now it's really the time for science, and also we can start playing with the formation. Thank you so much, and I will be happy to answer any question.
Any questions, Raphael?
I'm sorry if I missed it, but what's the metrology used to maintain the formation flying?
And it's where I have my backup slides. So actually, we have several metrologies. The first one is a relative GPS. So we have an algo taking GPS information from the 2 spacecrafts. And when we go through the perigee, maybe just to come back on this one, this is the orbit we have. So we have an apogee of 60,000 kilometers. So basically, the perigee is very close, 600, so we have GPS here. So the first part is to acquire the GPS and do double differentiation. Then we have vision-based sensors. So one camera on the occulter spacecraft will image cooperatively the coronagraph spacecraft, which provides already centimeters level accuracy. And the most important metrology we have, I would say, it's this one, which is called shadow position sensor. So it's a set of photodiodes around the aperture of the coronagraph, and they kind of scan the penumbra profile we have and help then the control to maintain the coronagraph centered in the umbra. And this one is a laser metrology, which is used as well laterally and longitudinally. So this is in infrared picture in the clean room there as well. So the laser is also, it shoots from the occulter spacecraft, reflected by a corner cube, and goes back in the occulter spacecraft for processing.
Bertrand Menesson, JPL. So what's the size of the aperture of the coronagraph spacecraft aperture?
It's just 5 centimeters aperture. Yeah.
So are there any talks at ESA or in Europe to use this experiment as a springboard to demonstrate starshade-like technologies for stellar coronagraphy?
Yes, so starshade is basically this one is maybe let's say a first step. Starshade, we are talking about tens of kilometers or even more, tens of thousands of kilometers. So this is another scale, but probably for this kind of sensor could be applied also for Starshade. The use of formation flying I would say everyone was a bit shy before, so everyone was like, maybe, maybe not. Now, maybe we can talk a bit about more new mission concepts. The idea of formation flying is that you can have a huge instrument. So here we are talking about 150 meters, but you can have huge instruments that is distributed over small spacecraft. So you can launch something in orbit. We can think about interferometers, synthetic apertures. We had this year at ESA an analysis was more for communications to create a huge antenna, for instance. X-ray missions as well because they have such a big focal length. So for Starshade, this is, let's say, one use case that was also studied in the past, I know, by NASA. And yeah, I think this one is just to pave the way and to show the mission concept.
Let's thank Raphael. Oh, one more. No. Sorry, missed. Last one.
Just following up on a partial answer to Dimitri's question, Simone D'Amico, who I think worked on the Proba-3 original orbit and formation flying, and I had a full-fledged Starshade demo in a small sat class, and NASA just was utterly uninterested in trying to do anything like that. It speaks well of ESO that you do these 100 million euro scale tech demos like this and like LISA Pathfinder, and it's kind of weird that NASA doesn't want to spend money to demonstrate technology on a large scale and flight, with the wonderful exception of the Roman chronograph, I guess. I shouldn't complain.
But yeah, maybe ESA is in a better position to do it now.
All right, let's thank Raphael, and let's thank all the speakers from today, this morning.